Good morning, everybody, or good afternoon or good evening, depending on where you are. Thank you so much for taking some time out of your day to join us live from the Bruker Lab. We will start the presentation in maybe about a minute or so. Just want to give some last minute stragglers the time to log in, get situated. So sit tight, we'll get ready to talk about polymers.
You want me to share my screen now, or you need to hand that over right when I get started?
I will hand it over to you.
Okay.
All right, 10 o'clock on the dot. Let's get ready. So, like I said, welcome, welcome. Very excited to have you here. First of all, I'd like to introduce our presenter today. We have Mark Arnold, who is a senior application scientist within the Applied Markets Division of Bruker, concentrating on polymer MALDI applications. He has over 20 years of experience analyzing synthetic macromolecules using mass spec methods. Mark comes to us after 14 years in industry at Xerox Corporation, followed by 3.5 years at Oak Ridge National Lab in the Center of Nanophase Materials Sciences. Mark will be presenting on polymer analysis today, live from the Bruker Lab. And I'd also like to mention that we'll have a brief Q&A at the end. So if you have any questions, feel free to shoot them into the chat box over here, and we'll address them at the end. So without further ado, let me hand the mic and the presenter over to Mark, and let's get this thing going.
Okay. Let's see. Okay, can everybody, Megan, see my presentation?
I can.
Okay, so again, I'd like to thank everybody for registering and coming in to watch this live from the lab. In today's live from the lab, we'll be covering polymer analysis. I believe there's multiple windows for the web application. So obviously I would want you to pay attention to what's happening on the screen and not so much to me, but you can take a look around as to what I'm doing, and I will change the camera view. So before I get started, we are coming from Billerica here in our demo lab. So a quick scan of the lab, if I can get the camera to work. So right now I'm sitting at the table for the Autoflex, which is behind me, the Autoflex Max, flanked by a timsTOF Flex. And if we go, so here we see some timsTOF and impact. And then as we scan around, we could see that there's a lot of instrumentation here. So to the right center, we could see the Rapaflex, which is our biggest axial MALDI TOF, and then to the left we can see a timsTOF. So now let's bring this back to me. And some analysis computers and the floor. And now back to me. So now if you resize your windows, and we could go to what's on the screen. So as Megan said, I'm a senior application scientist focusing on polymers and industrial chemicals using axial MALDI TOFs. And if I could get my slides to advance. So I know this is a live from the lab, but what I'd like to do first is go through a presentation. So it's going to be a presentation live from the lab, but in the next section, we will go to live data acquisition, processing, and kind of get a handle on the workflow. And then after that, we will have some time for Q&A, I hope. So in section 1, what I'd like to do is cover portfolio and specifications of our instrumentation, what we offer. Then I'm going to go through some slides that'll give you the definitions of what MALDI MS is, what a polymer is, matrix, the kind of laser we're using, the MALDI process, what time of flight is, how it works a little bit, sample preparation and targets, Poly Tools, which is our software for polymer analysis, and then define what a Kendrick mass defect plot is, and then MS, we're going to try to acquire an MS spectrum, which is fragmentation. And then I'm going to mention at the end of this section TLC MALDI, which we can't do because of time constraints. It takes about a half an hour to image a TLC plate. So here's our product portfolio, and again, resize the windows as necessary to see the presentation. So you can see this is pretty much all of the instruments that we offer. So here we have OA TOFs or Q TOFs, so orthogonal acceleration. So these aren't axial. So the ions would come in and then be accelerated 90 degrees into the time of flight analyzer. But this is ultra high resolution instrumentation. Then we have high resolution plus ion mobility. And then we have an FTICR for extreme super high resolution. This is our portfolio of axial MALDI TOFs. And again, what we mean by axial is that it's a straight line from the source to the detector, as you'll see when I show a schematic of the instrument. And then we offer a Microflex, Autoflex Max, which is our workhorse, the Ultraflex Stream, and the Rapiflex, which is our largest and high sensitivity resolution mass spectrometer. We also offer nominal mass instruments, triple quads. We have a complete software suite. You can see PolyTools, Metabescape, and Task. And then we also have some elutes and SPI. So this is for chromatography. So this is our axial MALDI TOF portfolio. Again, we have a Microflex available, Autoflex, the Ultraflex Stream, and the Rapiflex. And what you get when increasing from left to right here is you get an increase in speed, increase in resolution, increase in sensitivity, mass accuracy. But here we have, the Autoflex, which is, available in linear, reflectron, and TOF. It's about 2,000 hertz or 2,000 hertz acquisition speed for the laser, 200 hertz in MS mode, Smart Beam 2 laser, and up to about 500,000 molecular weight. The Ultraflex brings in higher speed and resolution, sensitivity. We go up to 1,000 hertz, collecting MS data. Again, Smart Beam 2 technology, up to about 1 million molecular weight. And then we can also do MS, instrument as well. And then the Rapiflex, now we're getting up into Smart Beam 3D laser technology. That gets you up to 10 kilohertz, 1 million molecular weight, and we can also do MS. So here are some key specifications. I don't want to rely too heavily on these, but there are some things that we need to pay attention to. So obviously, going from left to right again, we're increasing in the molecular weight that you can detect. We're getting better and better mass accuracy. Our scan speed, or how fast we can acquire data, also goes up. And then our sensitivity also increases. And then the mass resolution. So what you get going from one to other, depending on your needs, you can get higher and higher resolution, up to about 50,000 for the Rapiflex. And again, Smart Beam 2 technology, the Microflex, comes with a nitrogen laser. These offerings have the Smart Beam 2. The Rapiflex has Smart Beam 3D. And excuse me, I need a drink of water here. And so the Rapiflex offers true pixels, which is about the smallest we can get is about a 5 by 5 micron square for your imaging needs and a very high speed. And the Autoflex and the Ultraflex Stream can also. So now we're going to go into some definitions. So when I finish this presentation, you may not remember everything, but at least we'll all be speaking the same language, since I don't know everybody's background that's in attendance today. So what MALDI is matrix-assisted laser desorption ionization. So this is the ionization process. This is where we make ions. So all mass spectrometers have 3 basic parts to them. You have a source, you have an analyzer, and a vacuum system. There's different configurations, but every mass spectrometer has these 3 pieces. So again, this is the source where we're making ions. Time of flight, TOF just means time of flight. That's the analyzer. That's where we separate things based on their mass and their energy, or M/Z, the mass to charge ratio. And that's how we separate them. And then finally, send them to the detector for detection. MS just means mass spectrometry. And these are just some definitions that I pulled up or wrote down. Please forgive me if they're not in line with your analytical textbook, but we are doing mass spectrometry. So over the study of using energy to obtain information about physical systems and their components, slightly different than spectroscopy as an NMR. So first we're going to go through what is a polymer. A polymer is a Greek word. Polymer is a Greek word meaning poly meaning many, mer meaning part or unit. So many units, just straight from the word. The definition I like to use is a substance whose chemical and physical properties do not differ by the addition or removal of one repeat unit. So here we have, you know, a cartoon representation of a polymer. You have a beginning, you have the chain, and you have the end. And then you can also have a branched polymer and a cross-linked polymer. Now imagine that, you know, this polymer is a chain you're wearing or a bracelet. If you were to take that off, remove one link, reassemble the necklace, put it back on, you would barely notice that missing unit. It would still be around your neck, it would still hold a pendant, it would still perform the same way. It would just be one unit less, and we could add a link and it wouldn't really make that much of a difference. And this is the type of data that we're hoping to see today, you know, a nice distribution. So each one of these repeat units in the chain is represented by a peak that you observe in the mass spectrum. So if this is N, this would be N plus 1, plus 2, plus 3, and minus 1, minus 2, minus 3. So when I was first starting out a long time ago, people would define a polymer by just molecular weight alone. A lot of older chemists would say, you know, nothing below 1 million, nothing below 500,000 is a true polymer that is a specialty chemical. And some other terms that we'll be hearing today are about molecular weight. So I'm going to be referring to number average molecular weight, weight average molecular weight, and then polydispersity index. And you can see the formula over here. Now what this means is that it's the MN places emphasis on the number of chains at that molecular weight, while the weight average molecular weight takes into consideration the actual mass of those chains and how many there are. And the one thing that I'm going to point out is that, you know, there is a little bit of an Achilles heel when it comes to this type of measurement. Anything with a polydispersity, or MW divided by MN, over 1.5 is a little more difficult to analyze. We won't get this kind of clean Gaussian or bell-shaped curve. We'll end up with more of a Schultz distribution with high peaks at high intensity at low molecular weights, and then decreasing as molecular weight increases. And hopefully, when I'm acquiring data live, you'll see an example of that. So the M in MALDI is matrix. So all that really is a small UV chromophore that absorbs the laser energy. So these matrices have been around for a while. Some of the older ones for polymers are dithiol, DHB, and HABA. Things like CHCA, SA, IAA are used for biological materials. I have two favorite matrices that I use a lot. One is retinoic acid, and the other is DCTB. The real name is right here that I'm not even going to attempt to read, but that is usually my go-to matrix when analyzing polymers. So again, all the matrix does is absorb the laser energy. So this is a diagram about the, lasers that have been used traditionally and what we're currently using. I don't really need you to focus in on these laser profiles, but what I want to point out is that the nitrogen laser was the first offering when MALDI first came out. It's a little slow, it doesn't have a long lifetime, and has, you know, poor laser focus, only down about 100 microns. Now we're using neodymium YAG lasers tuned to the third harmonic, which brings that IR laser down into the UV range. So now it is compatible with the traditional MALDI matrices as well as any new matrices that might come out. What we do get is the ability to focus that laser down to 5 microns. It lasts a long time, and we get very fast repetition rates from 2,000 hertz to 10,000 hertz. It's got a very long lifetime and will last a lot longer than the nitrogen laser. So how MALDI works is, what we do is we dissolve our analyte, dissolve our salt, or some sort of charging agent, and then dissolve our matrix, and then take aliquots of those 3 solutions, mix them together, and then deposit a very small amount onto the MALDI target, which we see here that I'm holding up in front of me. And we allow those 3 things to co-crystallize on the target surface. The laser then fires, and through charging of the matrix, so all the matrix molecules become charged through Coulombic repulsion, Coulombic explosion lifts the analyte into the gas phase along with the cation, and then through ion molecule reactions forms a pseudomolecular ion that is then extracted and accelerated into the flight tube towards one of 2 detectors. And as you can see here, we could use protons from acids, we could use sodium, or silver, all depending on what the analyte is. Now, you're going to hear me refer to linear and reflectron while acquiring data. This is a cartoon representation of the instrument. And so what happens is we create ions in the source. They're extracted and accelerated down the flight tube. We can either A, strike the linear detector, or B, strike the reflector detector. And in the linear mode, we get high sensitivity and lower resolution because of spatial and or energy spreads of the ions. And then the length of the field-free drift region defines the resolution and the accuracy. So that is for higher molecular weights or greater sensitivity. We can also then turn on the reflectron and have those ions turned around and then reaccelerated towards the reflector detector. And what this does is corrects for the spatial and energy distributions, focusing ions of the same mass onto the detector so they all arrive at the same time, giving high resolution. And that is very important if you're looking at molecules that differ by, let's say, 2 hydrogens. If you're looking at hydrogenation or dehydrogenation, that type of high resolution comes in very handy. So we have different sample preparation methods. Today, I used the dry droplet method, which is, again, just taking aliquots of 3 solutions, mixing them together, depositing a small amount onto the target surface, as you see here. We could use a double layer method where we deposit the matrix, then deposit the analyte and salt on top of that. And then we could also do a sandwich method, deposit another layer of matrix to kind of shield your analyte from the energy of the laser. We have a solvent-free method, which is taking a powder and then mixing it with a powdered matrix. And then what I do is blend those together on the target surface using a plastic spatula, being careful not to scratch the surface or damage the surface of the target. We could then deposit a thin layer and then blow off using canned air or nitrogen the remaining material, so we have a nice thin layer on the target surface. We can use conductive tape to attach samples to the surface of the target, like you see these wires here, and try to get some spectra off of the surface of the wire. And we also have TLC and glass slide adapters, which we can see here, TLC adapter, the TLC plate fits in, and here is the slide adapter used for imaging. We also have pictures of them here on the slide. Today we'll be using one of our standard targets, the MTP-384. We're going to use the ground or matte steel finish. We have an anchor chip target plate, which if you have dilute solutions, when you deposit the solution on the surface, this little kind of dot here inside the well allows the solvent to evaporate and then kind of focus whatever crystallizes onto that small spot. So again, if you have a low concentration, you get a nice small spot where hopefully you can get a spectrum from that. We have our TLC adapter. Again, your TLC plate fits in here. We could then image the surface and not only have RF values, but then we can get definitive chemical information right from your TLC. This is the imaging target where you can put glass slides in there with your tissue sample and image those. And then we can also affix certain things to the surface of the target. And the main take home from here would be that we don't want any liquids or loose powders or loose materials going into the source. And then they could fall off, contaminate the source, and cause a lot of problems. So, thin layers of things that are affixed to the target surface. So I'm going to move into some software. We're going to be using PolyTools today. That is our software for the analysis of homopolymers. We have a third-party software that we use for copolymers that I will get into, and also can give you some information about the high molecular weight sample that I'll be doing. So really what we need to see here is that from Flex Analysis, which is our analysis software, it is a one-click export of the information into PolyTools. From there, it will then render a mass spectrum, a Kendrick mass defect plot, and here you have some parameters that you can adjust, the mass tolerance, the repeat unit, N groups if you know them, the cation, and then displayed at the bottom here would be all the molecular weight information for each of these series that PolyTools picks up. So here we have the N groups. Here you can see the residual. Now what that residual means is a mass that isn't accounted for by the mass of the repeat unit. So remember, this is a chain with a beginning and an end, alpha and omega, and the repeat unit is what's in between. And so this residual mass is representative of the mass of the N groups that's not accounted for by the mass of the repeat unit. And then from that information, once we get everything labeled, we can get MN, MW, so number average molecular weight, weight average molecular weight, polydispersity, and the degree of polymerization, which means how many, on the average, how many repeat units are in that particular distribution. So what a Kendrick mass defect plot really is if you were to take this mass spectrum that we see here, tilt it towards you and look down on it, we can then separate in a third axis based on that residual mass. Again, mass not explained by the repeat unit. And then we could see what particular masses are coordinated with those same other masses in that distribution. So here we have a distribution of distributions. We could see that, which one's the most intense. Peak intensity is related to the size of the dot here. But also what we can do is we could look for things that aren't the same as the polymer that we're interested in. So if you have a blend or a mixture, so here we're searching for an ethylene oxide repeat unit. We see we have two distributions that are polyethylene oxide or polyethylene glycol with different N groups. But also we have other polymers that aren't polyethylene oxide or ethylene glycol in this mixture, and those appear on the diagonal. So the horizontal lines are the ones with ethylene glycol. And then we're going to acquire some MS data. So what MS is isolating an ion, adding extra energy, and fragmenting it. And that would be useful if we cannot determine the molecular structure or the microstructure from mass alone or any type of trends that we observe in the mass spectrum. So we're going to, again, isolate that precursor. We're going to give it energy. It's going to fragment. We're going to detect those fragments. And then we could use those pieces to kind of reconstruct the intact parent ion. And this is an example of an MS spectrum. So here in this example, we have a ethylene oxide functionalized with a hydrocarbon tail. And from the mass spectrum, we can see that we break up this precursor, adding energy. We can actually see the loss of that hydrocarbon tail plus subsequent losses of the repeat unit. And from these pieces, we could then go back and propose a structure for that isolated precursor ion. And now we have the TLC MALDI. And again, this gets a mention because we do not have time to go through this in the actual live from the lab. So what this is imaging of your TLC plate, where normally under UV or staining, we would get these RF values, but then we would have to have, TLC of all the starting materials and everything else. But with the TLC MALDI, we can then image this plate. We get a heat map of the things that are located in, different distributions of things that are in these spots. And from there, we actually have mass spectra of these components in each spot. And we can also do MS, again, break these things apart. And in this case, for these lipids, verify the head unit of these particular lipids. So all from the TLC plate. Now, with that, I would like to move into the actual data acquisition and then, the workflow in the software and give you an idea of what it is that we do. So what I'm going to do is I'm going to step out and put the target in the instrument. So I'm just going to show you the front of the instrument while I do this. Okay, so getting the target in this particular instrument is quite easy. It's an automated, oops, what happened to my presentation? There we go. So it's automated actually. So you just put the target onto that tray, the tray takes it in. And what's happening right now while I'm speaking is that to transition from atmospheric pressure, oops, to high vacuum, we have to go into a lock. So what's going to happen is that the lock is going to pump, that is going to be at atmosphere. It's going to then put in the target. The lock is going to pump down, and then from the lock, the target will be inserted into the source. While that's all happening, now if you resize your windows, and hopefully you can see the acquisition software here, I'm going to walk you kind of through the basics of the acquisition software while that transitioning has happened from atmospheric pressure to high vacuum. So what we have here is a camera view of the target, and you will see it kind of doing a little dance in here as it inserts. It'll be moving around. We have a start button for the laser, saving spectra, clearing the sun buffer. We have a schematic or a cartoon representation of our target with letters and numbers. So all you have to do is click on the particular spot that you want. The target will then be positioned underneath the exact spot where the laser is going to hit when it comes into the source. And then we have some, generic information here about the target, the geometry, and the method file that we have loaded. And here we have, the detection range, and then some digitizer settings and the detector gain. So now the target is in, and what's happening now is it's still pumping down. And once everything is good, we'll have once the vacuum has reached a set point, everything will then a voltage will be applied to all the internals. And we can see that's ramping right now. So what we can do is go through, it's very easy to select a parameter file. It comes with stock parameter files. I'm going to use one of mine that I've slightly modified. And again, very easy to load a parameter file. And for axial MALDI TOFs, once you load a parameter file, everything is pretty much fixed. So the only thing you kind of have to adjust is your detector voltage and maybe the suppressor or the deflector to keep things away or out of detection for that spectrum. So what we're going to do is move to one of our samples, if I remember where I spotted it. All right, there we are. Okay, so here we see the co-crystallized matrix, analyte, and salt. Nice thin layer of crystals, very small crystals, which is what we like. And so what we're going to do now is start the acquisition. And now it's applying the voltage to the laser, kind of warming up. And then once that happens, we'll see in real time a spectrum, I hope. There we go. So what we see here is I do not have the suppressor turned on. So what we're detecting is matrix clusters, possibly clustering with the salt and our analyte. So what I'm going to do is set the deflector or the suppressor. So let's say mass 1200. Now what should happen is we can eliminate those clusters and matrix peaks from there. So what's happening is it's on timing. So as the ions exit the source, the deflector is on, pushing away all that low mass stuff, and then it turns off, allowing the rest of the ions to come through and strike the detector. So here we're operating in the reflectron mode. And we're looking, see we have high sensitivity, so the all carbon 12 plus 1 carbon 13 plus 2 carbon 13 plus 3 carbon 13, and superimposed on top of that is the silver pattern as 2 isotopes at 50-50 percentage. So I'm going to turn down the laser a little bit. We're going to go to the higher molecular weight side and kind of look at the data as we collect it, make sure that we're not using too much laser power where we're destroying the analyte, but we need enough to get decent signal. So once we're happy with the resolution and the signal to noise, we could start adding in these shots to the sum buffer. So what we're going to do is sum a bunch of shots, hopefully reducing noise while increasing signal. And once we're happy with the spectrum that we get, again, good sensitivity, resolution, baseline resolution in between all the isotopes, we can go ahead and save that. We would click Save As, choose the folder you want it to go into, give it a name, and this is a polystyrene MS 2500. And then there's comment fields where you could put in, concentrations of the solutions that you've used, the matrix, the solvent, things like that. In the interest of time, I'm going to skip all that. And we can go ahead and save that. So also what we're going to do is collect a spectrum of a polycaprolactone. And this should give you an idea of the broader molecular weight. So here we see with this blue spectrum, we have a nice narrow polydispersity, again, MW divided by MN, and a nice Gaussian or bell-shaped curve. But with this second analyte, what we're going to see, let me reduce the suppressor. There's some ions that are obviously coming out a little earlier, so let's take this down to like 800. So what we're seeing here is, again, a larger polydispersity, and also this is bimodal distribution. What I mean by modes are there's two high points or two center points, but we see that we have, high peak intensity peaks at low molecular weight, and then that intensity is decreasing as we get to higher masses. So slightly higher or higher polydispersity than the polystyrene that we were analyzing. So what we're going to do is zoom into a portion of this. And again, we're going to optimize for signal and resolution. As we acquire the data, that's what we're looking at. We want to make sure that we're using enough, so we want to be at threshold, what they call threshold. So enough laser energy to get a spectrum with good sensitivity and resolution, but not so much laser power that we're destroying the analog. So just above threshold. Once we're happy with that, we can save it again. So this is a PCO, polycaprolactone. And also, what we're going to do is a very high molecular weight sample. So here again, it's very easy to switch your parameter files. No, we don't want to save it. So we're going to go to one of the stock parameter files. Now this is the linear mode. So now we're doing high sensitivity, lower resolution. And if you want to make the baseline a little wider, we can go out to, let's say, 300,000 molecular weight. We move to our sample, looking for a nice smooth area to acquire the spectrum. Let's laser power a little bit. There we are. So again, very fast data acquisition. So here we're seeing 100,000 molecular weight polystyrene. And if you look at it close enough, we can see that we have a peak at 50,000, which is the doubly charged. This molecule is large enough to hold on to 2 silvers. And then we also have the silver-bound dimer at 200,000 molecular weight. So here you can see that we don't have that type of resolution we had at the lower molecular weight in the reflectron mode. It's a broad peak, kind of reminiscent of a GPC trace. However, it is an absolute molecular weight. Again, we were creating pseudomolecular ions, so a molecule with some sort of cationizing agent, and then we're detecting that, but we don't have the repeat unit definition that we had in the lower molecular weights. So here it's just a broad. Now we could play with this for a while and try to get that type of oligomeric resolution where we'd see the spaces in between for the repeat unit. But again, in the interest of time, I'm just going to collect some data. And we call this PS 100K. Oops. Okay. Now, I said we were going to do some MS. So I already have some preloaded data of these exact samples that, we're analyzing. So just to save on time. So the first one we looked at was a PS 2500. Again, this is the type of distribution that we saw. So there are various ways to do this. We can have it annotated, so that's very easy to do. Just have to make sure we have the right parameter files, which we can set up here. So we find our mass list, but let's say we didn't know what this was right away and we wanted to do MS. So we could select a mass. Let's say I'm interested in 2038. We could highlight that mass, say mass list, MS list. We could click on that mass, add to the MS list, and then we could go into flex control. Now we're going to choose that lift parameter file. So lift is the name of the parameter file that we'll use to acquire an MS spectrum. Now, while that is loading up, so we have to wait for the vacuum to get settled, the voltages to apply, and while that's going on, I'm going to go ahead and send this to flex control. Or we could just remember the mass and type it in, but if you have multiple samples with multiple masses, you want to do MS, this is a very easy way to do that. And as we see here, once we sent that mass to flex control, it's in this pull down menu for the parent mass. Now, when I put this in, it's going to move. I actually have these samples on a different spot. But the software will take you right to the spot that you acquired the data on, but we were down here. I acquired that data yesterday. So once we arrive at our spot, parent ion, we're still waiting for the voltages to ramp here. I do a little different. I like to manually pick my peak. Okay, so now once everything says ready, we're good to go. What we're going to do now is go back, make sure we have parent ion clicked. I'm going to find a nice fresh spot. And we're going to start collecting some parent ion data. So what we're doing now is isolating. Everything else is being deflected away from the detector except for that parent ion that we're isolating. We're going to add that in, take another one, add that in, and then we're going to say fragments. I'm going to pick my all carbon-12 isotope as the parent mass, move to a fresh spot. Now, what I do is a little something different than some other people do. I actually clear the sum. I want to detect my fragment ions first. The old rule of thumb was when doing MS spectra is to acquire enough fragments to reduce your parent signal by 50%. So I want my parent and my fragments to be, or my precursor and my fragments to be on the same scale so we see everything. So that's why I kind of like erase that parent ion spectrum. And now I'm going to go into the fragments. After I'm done with the fragments, I'll add the parent back in, and hopefully everything will be on the same scale. So we're starting to see some fragmentation. I know for a fact that this needs a little higher laser power. Okay, once we have enough laser power, I'd like to zoom in and check out the fragments that are being detected, make sure we have good sensitivity and resolution. And what I usually do is give it a little smooth and then add it into the sum buffer. Smooth, add it in. And you repeat this process until you're satisfied with the spectrum that you've obtained. And then once we're happy with that, now I'm going to switch back over, add my parent back in. And maybe one more just to get it up a little bit higher. And there, so now we have our parent and our fragments all roughly on the same intensity scale. That way one thing isn't like super tall and the rest are kind of down, what appears to be down in the noise. And we could save as okay. Now we're going to move back into flex analysis. Get rid of this. So what we do from here is, again, what I like to do is kind of look at my data before I go any further with the analysis. I kind of see what the spectrum has in it, what peaks are real and not real. And by not real, I mean a peak that looks like this, that is broad and unresolved. That's more than likely some sort of fragmentation that's occurring in the source. So it's got a lot of kinetic energy spread, so we're not seeing the isotopes. So if that gets annotated later on and pulled into polytools, you know, I kind of know that there's at least one distribution of peaks in here that we really don't need to focus on. So after we get spectrum annotated, we could go in and look at it with this annotation tool. And what that does is draws either the distance between peaks, here the mass of the repeat unit, it is styrene, it should be 104.06, we're seeing 104.05. We can also switch that to polymers. And then if we do it again, it will label those peaks as polystyrene. And we can do this for every sample that we have. And again, to annotate peaks is very simple, find mass list. Now, once we get everything annotated and we're happy with that, we could go right into polytools. And again, what we're seeing is a, you know, intensity, the integrated spectrum, the full distribution, and then the other peaks are being annotated. And so what we want to focus on right now is just the main distribution in the interest of time. So I'm going to say we can get rid of the unassigned if we wanted to, just clean up the Kendrick mass defect plot view. So I know for a fact that this is a polystyrene. I know that it has the silver as a cation. And then we end up with several distributions. And then what polytools is doing, and so we have, you know, the match, I have the mass tolerance I have set pretty high. We can put in the repeat unit, the cation, but we're trying to determine what the N groups are. And then we have various ways to switch from integral to peak height. But what polytools is doing is, it's, since these are in the polymer tables that can be edited with your own N groups, repeats, whatever, it's venturing a guess as to what this first distribution is. And so what it's saying is it was initiated with a butyl, terminated with a hydrogen, and then it knows that we have a silver cation. And really, in real life, that is exactly how the polymer was made. Sec-butyl initiated, anion polymerization of styrene, terminated with a proton. So once we're satisfied with that structure, we could either type whatever we want in, or we can use from the pull-down menu. So once we enter those N groups into polytools, this residual should come to 0. Now we've accounted for all the mass, not just what's going on with the repeat unit, but also the mass from the N groups. So that residual mass should be close to 0 or 0. And again, for that main distribution, which is all we're really concerned with in this particular sample, and if you want to clean that up, you can delete the rest of those. And what we have here is, you know, MN of 2472, MW of 2574, poly dispersity of 1.4. We're accounting for 92%, 93% of the intensity for the whole spectrum. And we can then export that to a report. If I remember where it is. Oh, nope, wrong one. And there would be your report that you could export, and, you know, your job is done and the workflow is, you know, that simple. And we're going to go through it again for the polycaprolactone. Here's that PCl that I acquired. And again, this is for homopolymer. Now, within the interest of time, if I can get there, we will show it again, but we could do the same thing. Tools, polytools. And we could go through and start to assign the N groups to that. So now I'm going to move on to, now what if we have a copolymer or very large molecular weight samples? So for the large molecular weight and the copolymer, we're going to move into polymerics, which is our third-party software. If I can get it started. And again, I don't have time to showcase everything that this software can do. So the first thing we're going to do is pull in the very large molecular weight polymer that we did. Now, we don't really even need to enter a lot of information about this polymer, but what we could do is say, okay, we know that's 100,000 molecular weight. We know that this is a doubly charged at half the mass. We know that this is the dimer, gas phase dimer. So we could say all we're really interested in is from like 65,000 to 140,000. It will eliminate the rest of that spectrum, and we could just go right into homopolymer analysis and get the MN, MW, MZ polydispersity without entering any information. So this is a way we can analyze that high molecular weight data, focus in on certain peaks, and then get the actual mass that we are looking for from this type of mass spectral data. But we can also bring in a copolymer. Now, PolyTools doesn't handle copolymers, but Polymerics does. And that's kind of, I'm not going to go through all the processing that we would see here. So I'm just going to go ahead and open up something that I had already done. Hope it's still there. We can go into the copolymer view, and what we see here is a very complicated, type of spectrum, and there's a lot of chemical information here, but from after determining what the end groups are, it's just simply H on one end, OH on the other. We have two repeats, ethylene glycol or ethylene oxide, propylene oxide. And the main takeaway here is it will go through all the chain statistics, calculate everything. And what we see here for this odd kind of isotopic pattern is that we actually have overlapping copolymer signals within the same isotopic envelope. And what the difference is we see here, these two Dalton differences are the addition or removal of triads and tetrads of repeats. So 44 ethylene oxide times 4 is 176, 58 propylene oxide times 3 is 174, and that's where we get these two Dalton differences. So here we're gaining 4 ethylene oxide and losing 3 propylene oxide, and again here, and then we can also go backwards down to that there. So this is how we would handle copolymer analysis or getting molecular weight from very large ions or very large distributions in the mass spectrum. And then finally, what we could do is also use PolyTools to analyze MS data. Here is the MS data for that 2038. I already have the spectrum annotated. We could pull that into PolyTools. So it is a way to look at that, and hopefully it works. We're going to tell it what it is. Say fragmentation spectrum of polystyrene with a silver. And we might have to switch to peak height if it's having a problem with the integrals. We could turn that off. And now what we're doing is we're seeing that through this, we have peaks that are actually in the same series. So all of these peaks have the same end groups. And now we can kind of put together what is happening in this MS spectrum, and from this residual mass, start to analyze what's on the ends of these very short chains, the fragments from the precursor ion, but what's on those ends. And we can also do it for very high molecular weight. So here is a spectrum that I collected off a different instrument, the Rapiflex. This is an MS spectrum of a molecule at almost 6,000, so 5,680 molecular weight. And again, we have several distributions, and we can see here that maybe, even these fragments are similar to, the structure of the parent, since they almost have the same kinetic mass defect. And again, we go through here, and we could start to put together the pieces of what we see, and then hopefully gain some information about that precursor. And with that, I believe we are done. I think I showed everything. So I want to leave some time. It's 10 till, so I want to leave some time for questions and answers. And hopefully you got an idea of what the workflow is, how we acquire data, how we analyze it, get it into these types of processing software, and get some answers for that particular material.
Thank you, Mark. Thank you very much. Great presentation. Appreciate the demonstration and walkthrough. We have a couple questions here in the chat box. I'll start with the shortest. What are limitations to MALDI?
The overall, there's actually could be several. The biggest one is, again, what I discussed during the presentation, which would be the polydispersity. Without going into it too much, imagine that distribution. If everybody could still see the processing software, I don't know, do they have this view still?
Yeah, I can still see it, yeah.
So without going into too much detail about how detectors work and everything like that, so imagine that, you have here what would be, I don't know, 142 peaks. And all of that signal from the sample is contained in these 142 peaks in this kind of like narrow molecular weight range. But that polydispersity, once that distribution starts to get wider and wider, imagine the same amount of signal spread over a larger area on the x-axis. So then all these peak intensities would start to decrease. And then you get to a certain point where everything's kind of driven into the noise. So that polydispersity is very important. So polycondensates, polyethylene terephtalates, things like that are condensation polymers would have that type of broad polydispersity, making it more difficult to analyze. But there are things you can do to overcome that: collect fractions, analyze each fraction, and then that will give you the structural information at certain molecular weights that you're looking for.
Thank you.
Oh, and it's also theoretically mass unlimited, but getting up to higher and higher masses is quite difficult, and it takes a lot of experience and time to get the sample prep right. So if you're going to do a 700,000 molecular weight polymer, you might have to do a dilution series, figure out the right matrix to analyte ratio, and then you might have enough sensitivity to do that, but it is difficult and requires a lot of time. So it's not truly unlimited in practical application. Anything, above a certain molecular weight is going to be difficult without advanced sample prep.
Sure, we just got another question. How do you pick the best matrix?
Really what you're looking for is, trying to match possibly the structure. So if you're going to do something like a hydrocarbon type material, let's say a pitch, or something that has a lot of conjugated rings, you might want to try something like anthracene, triol, or dithronol. If you have, a lot of amines, you might want to pick a matrix that is, functionalized. So kind of the polarity and the structural similarity to the analyte would be the guide. More neutral matrices like DCTB seem to work with a lot of like a wide range of polymers. But again, if you're looking at carboxylic acid functionalized materials, you might want to pick an acid type of, matrix. So it's just kind of aligning that polarity. And then also it's, you might want to choose, if you're trying to fragment, there are matrices that are considered hot, which transfer a lot of laser energy to the analyte. And then you have cooler matrices, quote unquote, where there is not a lot of energy transfer to the analyte. So then you would look for those types of, relationships, and depends on what it is you're actually trying to do. But I would go for structural similarity and polarity and try to match that to your analyte.
Thank you. All right, following that question, what is the minimum required amount of sample for examination?
For polymers, I would say on target, really you only need about 10 milligrams, and that makes a mil of solution. And then from that, we're using 2 microliters. And then from the mixture of analyte, salt, and matrix, we're only spotting a half a microliter. So theoretically, we're down into the attomolar or 10 to the minus 15th. But I would say 10 to the minus 12, 10 to the minus 15 on target should be enough to get you a spectrum, way more than enough to get you a spectrum. But theoretically, when they calibrate with biomolecules, we're talking, minimal detection limit, under perfect conditions could be down to zeptomolar detection range.
And to follow up with that question, what is sample preparation like if my polymer doesn't go into a solution?
Well, when I was going through the presentation, I mentioned solid sample prep. And so you could either mix your matrix and possibly a little bit of salt and your powder, your sample in a centrifuge tube, stir it up, or what I do is just, again, mix it on the target surface, kind of blend it together with a plastic spatula as not to damage the target surface, hopefully get a nice thin layer on the target surface, blow off the excess, and then you can acquire MALDI spectrum from the thin layer of solid material that you deposited on the target surface. But that works for, again, like pitches that I've been analyzing, functionalized waxes, things that don't go into solution very easy. That's solid sample prep. And if your sample is gooey or sticky, you could also you could freeze it and then do it on a frozen sample where you get more crystalline nature, and then allow that to come to room temperature, put it into the instrument and acquire a mass spectrum there. So you can cryo blend your samples if necessary.
And I have another question. Is it a non-destructive method, question mark? Parentheses, sample can be retrieved, question mark?
No, it's a destructive method. So what we're actually doing is, you could recover what you didn't ablate with the laser, but once it's ablated and transferred into the gas phase, it's gone. And then if you try to recover that sample, you would just have to remove any matrix or salt to recover a pure sample. But again, we're using very, very small amounts. So if you had, only 5 milligrams of total sample, you could put that in the solution. And again, you're only pulling a 2 microliter aliquot or 4 microliter aliquot from that solution. And then, the rest of, 100 microliters or a milliliter, you're retaining 998 microliters of a 1 mil solution. So again, very small amounts. So you don't even really need to dissolve all that much.
Thank you, Mark. Got a couple more coming in. Can we analyze biopolymers such as carbohydrates, lipids, proteins?
Yep, that is a big application for Axiom MALDI TOF, OA TOF, the TIMS TOF that you see behind me. Yes, those are all amenable to the MALDI process. Again, just choosing the matrices that are more suited to biological applications, and then you spike in a little acid for, proton donor. But yes, biopolymers, lipids are done all the time. The NIST websites have, sample preps for those, as well as our website. But yeah, I mean, just the TLC MALDI was a lipid example that I showed during the presentation. That's been the bread and butter of Axiom MALDI TOF for years.
Here's another. Will MALDI TOF be able to identify branched polymer?
Yes, depending on what you are calling branched, if it's a dendrimer or a star or things like that. But if you're talking extremely high molecular weight with branching as far as, a network, that's a little more difficult with some sort of degradation prior to MALDI, because we can't desorb and ionize a complete network of chains. So yes, with some branching, it is possible to do that. But once that branching goes from just, dendritic or star or just a few branches to more of a network, then, that obviously becomes more and more difficult without some degradation prior to analysis.
Got a long one here. Can MALDI be applied to identify fungal plant pathogens as it was reported for bacterial identification? If yes, what species? Here we go. If yes, what species are available in the library? Question mark.
I have absolutely no idea. I'm going to say yes. I am a polymer and industrial chemical expert. I have little to no experience in biological applications, but if it was done for a different class of compounds, I'm assuming it could be done, but that question can be forwarded, kind of up the food chain, even to Germany, and we could get back to you with an answer. But it's a little out of my wheelhouse to answer a question like that. Again, I am synthetic macromolecules, not biological. I apologize.
That's right, Mark. We don't expect you to know everything. That's impossible. You're good. You're doing great. How about this? Is the polymetric tool providing peak assignment, like proposed structures?
Poly tools will give you its best guess as long as you've already edited the Polymer table that is kind of in the background of that software where it pulls in those structures. It will offer a best guess as long as you put those structures into the Polymer table. However, we do not have a searchable library like they do for like peptides or proteins or whatever. And polymerics, you could use the software to help determine what the end groups are when the peaks get fitted into, like, if I still have it pulled up. So when these peaks get fit, if depending on what the end groups are, if you have something that doesn't line up, let's say here, it's going to be off center from that peak. But again, in polymerics or poly tools, there's no searchable library. You kind of have to have determined the structure already, or working on determining the structure of polymerics, or have entered a lot of different end groups, alpha and omega and cations, into that Polymer table, but there are not searchable libraries. But then once those structures are in there, it will fit the data for you. It'll pick the peaks and fit each distribution.
Excellent. Thank you very much, Mark. And it looks like that is our time. If we did not reach your question, please feel free to just send us an email and we can go further into detail with any questions that you may have. Again, I'd like to thank Mark, our presenter, for going through this very thorough analysis and live from our lab. And thank you all for taking the time out of your day to watch and learn. And maybe I hope you learned a few things. And if you have any more questions, again, please feel free to email us. If not, hope you have a nice day.